Okay. Yeah. Before the ordinal, I think we finished with the linear probing. Okay, so the linear probing, we want to put the data, we want to put the item into a cell with the linear space. The linear space means whenever we find a blank, so we put the item. Okay. However, as we already know, with this linear probing, there might be several steps. For example, when you need to put the item in the index 5, but if all next item is already full, then you will go to the last item with the linear space, or we call this is n, almost n time. So we want to avoid n times. Therefore, there is another way to do this collision problem with double hashing. So the double hashing, we call it double, means we have the secondary second. So it is the not the first, but we want to find the second function or the secondary hash function. We call it decay. And it handles collision by placing an item in the first available cell of the series. So we have the first. If the first fail, then we check the second. 첫 번째는 실패하면은 두 번째 체크하고. So the function will be like this one. I plus j multiply by the decay. So decay is the secondary hash function. And again, we do the mod. Mod means namoji, remaining. So we want to find the remaining of the value with n. N is the number of the place. J is a number from 0 until n minus 1. So we will check how to calculate this one. The secondary hash function dk cannot have 0 values. So here, the dk cannot have 0 value. So dk cannot be 0. And the table size n must be a prime. Okay, prime means any number that can be divided by 1 and its own number. Then 2, 3, 5, 7, 11, 13, 17, and so on. So those numbers are the prime numbers, okay, and so on. The table size must be a prime to allow probing of all the cells. So there are some kind of choice for the compression function. So if you still remember the compression function, so if in the first part we have the compression function, we just do the k mod n. Okay, so we just do the remaining value. But for the secondary hash function, we have d2k. So this is the meaning by the secondary equals to q minus k mod q. So q is any number which is a prime, and it should be less than n. And the possible value for the d to k are 1, 2, and so on until q. Let's see with examples. I think it is better to see with examples. Now, we have the data like this one. So we have 18, 41, 22, 44, 59, 32, 31, and 73. The problem now, consider a hash table storing integer keys that handles collision with double hashing. So double hashing, what is double hashing? We have two hash function. This is the first hash function, and this is the second hash function. Now we want to put this key into this hash table. This hash table, we have 13. Okay. N equals to 13. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, we have 13 space. Now, K is the key. So we have 18, 41, 22, 44, 59, 32, 31, and 73. So we have this one. 18, 41, 22, 44, 59, 32, 31, and 73. We have HK. HK, this is the first function. So the first hash function. And then DK. DK is the second hash function. Now, how to calculate the HK? HK equals to K mod 13. Then 18. 18 mod 13. What is the value? The value is 5. Okay. And then we have DK. DK equals to 7 minus K mod 7. So this is the function that we define based on the definition here. Okay. So we have the compression function, we have this formula, and yeah, we can just use any prime number for the Q, but K is the key. Then we select 7 as the Q, and K is key. Now, if you look at this DK, then we have 7 minus 18 mod 7. What is the value? 7 minus 18 mod 7 equals to 4. Then it is 3. So the value is 3 will be here. Okay. Now, what does it mean by proofs? Proofs means we have the first value from the first hash function. We have the second value from the second hash function. So we will select the first. We will select here, and then we put 18 in the position index 5. So we put 18 in the index 5. Next, we go to the value K equals to 41. 41 mod 13. 41 mod 13 equals to 2. Okay. And then we use the decay. Decay is 7 minus 41 mod 7. Then this is 7 minus 6. Then we got 1. So 1 is the value at the decay. Now we check. What about the position index 2? Okay, in the index 2, nothing. So we put the 41 in the index 2. Next, we go to the position, the key equals to 22. 22 mod 13. Then it is 9. With the secondary hash function, 7 minus k 22 mod 7. Then it is 7 minus 1. So the value is 6. We put 6 here. Now we have 9. So let's see, in the position 9, the first value is in the 5. The second value is in the position 2. The next value is in the position 9. So 9 is empty. Then we put 22 in the index 9. Next, we have 44. 44 mod 13. Then this is 5. Okay, we put 5. And then decay. 7 minus 44 mod 7. 44 mod 7. 7 minus 2. Okay, then we have 5. So we put here as 5. Then we choose 5. Okay. We choose 5 for the proofs. However, as you know, 18 already select 5. So in the position 5, we have a value which is 18. So we cannot put 44 in the position 5. Okay, then we check the secondary value. The secondary value is also 5. So we cannot put also in the index 5. Then what should we do? We have this function. Okay. I plus j multiplied by dk mod n. So it means if the first j, if we start with 1, then we can go to the next j when j equals to 2. So what does it mean by j equals to 2? So we have I plus j dk. Oh, sorry. I plus j multiplied by dk. Now we have the first one I is the first value, which is 5, okay, 5, plus when j is not available, okay, when j is 0, multiply by 5, then we put into the cell 5. But 5 is already available with 18. Then let's go to j equals j equals to 1. If j equals to 1, then it will be 5 plus 1 multiplied by 5. Then means it will be 5 plus 5, then it is 10. So we will go to the next, which is 10. Check the 10. Okay, the position 10 is empty. Then we put 44 in the position of 10. Next, we have 59. 59 mod 13. 59 mod 13, it is 7. Okay, we put 7 here. And then 7 minus 59 mod 7. Then we can get the value 59 mod 7. It is 3. 7 minus 3, then it is 4. So 4 is the value here. So actually we can do with the previous one, okay, 7 minus, we have 7 plus 0 multiply by dq mod n. N is the size of the table. So because we have only the 13, so we don't need to consider that one. Because if you 5, yeah, 5 mod 13, of course it is 5. Okay. So I will not consider this mod 13. If you look at this one, 7, it means we have 7 plus j. When j equals to 0, 0 multiplied by 4. 0 multiplied by 4, it means we will consider 7. So 7, let's see, in the 7, there is still no key. Then we put 59 into the position 7. 32. Okay, same. 32 mod 13. 32 mod 13, it is 6. Okay. And then we have another function 7 minus 32 mod 7. So 32 mod 7, it is 4. So 7 minus 4 equals to 3. So 3 we put here. When we have a 0, okay, so 6 plus 0 multiplied by 3. Yeah, of course it is 6. Then we check the position 6. In the 6, okay, so there is still no any key in the position 6. Then we put 32 in the position 6. Now 31. 31 mod 30. Then this is 5. Okay. And then 31, 7. Okay, anyway. 7 minus 31 mod 7. Okay. Then it is 7 minus 3. Then it is 4. Then 4 we put here. Okay, now we check when j equals to 0. When j equals to 0, so we have the 5 plus 0 multiplied by 4. Okay, let's see the position 5. What is the position 5? The position 5 has been filled with 18. Okay. Then we need to go to the j equals to 1. So when j equals to 1, so 5 plus 1 multiplied by 4, then it equals to 9. Okay. Then the second will be 9, but 9 has been filled with 22. So what is the next? Then we go to the next j. J equals to 2. So 5 plus 2 multiplied by 4. Then it is 5 plus 8. This is 30. Now, based on this one, we have the mode n. Okay. So mode n means this value cannot more than 12. So yeah, actually, if you do this one, this is 5 mod 13. 5 mod 13 is 5. 9 mod 13. 9 mod 13 is 9. 13. 13 mod 13, it is 0. So we consider 0. Now let's see 31. We can do the probes in the position 5, but the position 5 has been filled with 18. Next, we can put the 31 in the position 9, but position 9 has been filled with 22. So we go to the next, which is 0. Is there any 0? No. Then we put 31 in the index 0. And then the last one, 73. 73 mod 13. 73 mod 13, it is 8. And then 73, sorry, 7 minus 73 mod 7. 73 mod 7 is 7 minus 3. Then this is 4. Okay. So we have 8 and 4. 8 plus 0 multiplied by 4. Then it is 8. Let's check the 8. No key in the position 8. Then we put 73 in the position 8. So the full hash table will be this one. So every key will be inserted into this hash table. Okay. So this is using the double hashing. We have two functions like this one. In the worst case, the search insertion and removals on hash table, it takes on time. So we have on. The worst case occurs when all the keys inserted into the map collide. Okay, so we know the meaning collide. If every key collide, then yeah, it will take on time. So like this one. If this one, this one, this one, they do not collide, then it will take or n time. Okay. But if it collides like this one, it collides, this one, it collide, then yeah, you need to minimize this collision. In order to minimize this collision, we can use the double hashing or we can use the linear probing. If you use the linear probing, it will be until n times, so n multiplied by n, so it means it will be n power of 2. But with the double hashing, we can minimize the searching. So we call it, this is the load factor. The load factor means A equals to N divided by big N. So N is the number of the data that we want to input, and then N is the size of the hash table. So in the previous example, we have 1, 2, 3, 4, 5, 6, 7, 8, and N equals to 8, and then big N. Big N is the size of the hash table. The size of hash table, it means we have 13. And the load factor means this is A equals to 8 divided by 13 in the previous example. Assuming that the hash values are like random numbers, it can be shown that the expected number of probes for an insertion when open addressing is this one. So we have 1 divided by 1 minus A. So if A is 8 divided by 13, then yeah, you can calculate 1 minus 8 divided by 13. So this is, we call the expected number of probes. And when we do this one, the expected running time of all the dictionary ADT operation in the hash table is O1. So O1 means we just have, when we insert, we expect it is one time or constant. In practice, hash or hashing is very fast, provided the load factor is not close to 100%. So if you look at this one, so the performance will be very good. And yeah, unfortunately, this one is applicable when you do with the small database. Small database means, yeah, if you deal with the small data, it is okay. But if your data is very big, yeah, this is not okay. Compilers. So the compilers, for example, if you use Python, actually Python compilers is based on the C language. So the compiler from Python to the C language, yeah, they use this kind of hash function. And browser cache, it happens in the internet. So if you do the internet browsing, yeah, usually they will use this kind of way to save the data. So the next section will be about the tree map. So in this case, I'm going to explain only about the binary search tree. The concept of the binary search tree, we follow the total order relation. The mathematical concept of the total order relation, it uses this symbol or less than equal to. And there are three properties. The first is reflexive property. We call reflexive property means that when we have x, it is equal or less than x. X is less than or equal than x. And then we have anti-symmetric properties. The anti-symmetric properties means if x is less than or equal to y and y is less than or equal to x, then it means x equal to y. This is, we call it anti-symmetric. And we have the transitive properties. The transitive properties means we have x is less than or equal to y and y is less than or equal to z. It means that x is less than or equal to z. Okay, so we call this is the total order relations. In the order maps, we assume the keys is a total order. The total order, maybe the simple way to say the total order is using the number like 1, 2, 3, 4, 5, 6, 7. So this is a total order. And then items are stored in order by their keys. So we want to check the keys, and then with the total order relation, we will set the key. This allows us to support the nearest neighbor queries. Nearest neighbor. It means we want to find what is the value nearby. So if I know that 4 and 5 is near, then yeah, I will use this nearest neighbor problem. It means that item with the largest key less than or equal to k, item with the smallest key greater than or equal to k. So we will check this one. As you may know, in the search, in the first part of our lecture, you learn about the search. We can do with the linear search. When we do with the linear search, it means we search one by one. If we have the array, then we search from the index 0, and then we move to index 1, and then we move to index 2, we move to index 3, index 4, and so on. Then we will do this one for n times, or the big O performance will be On. But in the binary search, as you may know, that we can reduce the number of searching. And we can use the binary search using the nearest neighbor queries of an order map. So order map means once you have the key, okay, when you have the key, so you will sort at the first time. So this key is already sorted. If you already sort this key, then you can do the same like what we already learned in the binary search. So last time we learned about the high-low. Okay. What is the high-low? It means we want to find the middle value, we want to find the low value, and we want to find the high value. So we want to find the high, we want to find the low, and we want to find the mid value. At its steps, the number of candidate items is half. So for every step, we will do half. So this is the total, then we do the half. 10 minutes after O log n steps. It means after we do the searching, let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 elements. Then at least we have log n. So log 13. Log 13, let's say this is log this 2, 13. So maybe it is about 3 something something. 3 something something. Then it equals to maybe 4. So you don't need to search until 13 times, but by only 4 procedures, you can search. For example, I want to find 7. Then I have low mid, and high. Where is 7? 7, is it lower than 8 or higher than 8? We know that 7 is lower than 8. Then let's just choose the half. Let's just choose half from the 8. So this is the L, and this is the new high, and then this is the mid. Okay, this is the low, this is the high, and then this is the mid. And then check, where is 7? 7, is it lower than 3 or higher than 3? Because I know that 7 is higher than 3, so I limit again. Then this will be the low, this will be the high, and this will be the mid. And then I check 7. Where is 7? 7 is higher than 5 or 7 is lower than 5. We know that 7 is higher than 5. Then we put here. So L equals to M equals to H, and it equals to the numbers that we want to search. Then we have only 1, 2, 3, 4. So we have only 4 times to search the number 7 using the binary search. So the idea of the binary search we can implement in the search tables. What is search table? The search table, it means that we are using the order map. Okay. Order map is a map that has been ordered, and then it is implemented by means of a sorted sequence. So it's already sorted. And then we store the items in array-based sequence sorted by the key. And we use an external comparator for the keys. Okay, so external comparator, it is just like the symbol less than, equal. As we know, if you search the value, it will take O log n. So you don't need to go until n times, but you can just do log n. When you insert a new item, it will take on. Since the worst case, we have to shift n divided by 2 items to make room for the new item. And also removing one item, it will take on. Because the worst case, we have to shift at least n divided by 2 items to compact the items after the removal. Again, the lookup table, okay, we have this one, search table or the lookup table is effective only for order maps of small size. So again, this is only for the small size, or for maps on which search are the most common operation. So whenever you have a very big data, you can put the data into the search tables if your function is mainly about search. While insertion and removal are rarely performed. So for example, the credit card authorizations. So if you are working on the credit card company, if you are working in the bank, yeah, the credit card authorization will be good using the search table. So in the map operation, I think you still remember, okay, we have the standard map methods, for example, MK. So I want to get the value V. I want to get the value V from the map M if the value exists. If the value does not exist, then show the error. MK equals to V. So I want to update the value in the key K with the value V. So they associate value V with a key K in the map M, replacing the existing value if the map already contains an item with the key equals to k, and delete mk. So it means I want to remove from map M the item with the key equals to k. So we already learned this one last time. So the sorted map ADT includes additional function guaranteeing that an iteration reports key in the sorted order. Sorted order. So it means the key should be in the sorted. So 1, 2, 3, 4, 5, 6, 7, and so on. Okay. And there will be additional search, for example, find GT and find the range. Find GT. GT means greater than. So we want to find a value greater than k. So we want to say this one, find GTK, find greater than k. Or we can find the range. Find the range, what is the starting point and what is the stopping point. Okay, so we call this is find the range. So in the binary search trees, we have this kind of properties. Binary search tree is a binary tree storing the key. Key means the key value items following the map or the dictionary. And this is the node. So this is the node. Okay. And satisfying the following property. Let U and V and W, those are the three nodes. And U is in the left of subtree of V. And W is in the right of subtree of V. So we have the key of U less than the key of V less than equal to the key W. So I can draw like this one. This is V, and then I have U, and I have W. So U, the key of U will be less than or equal to the key of V. And then the key of P will be less than or equal to the key of W. Okay, so this is the condition. And the external nodes do not store items. Instead, we consider them as node. Okay, in the exam, the mid exam, you already understand about the tree. Okay, we have the internal node. This is the internal node. And we have the external node. Okay, this is the external node. The external nodes, this one, this one, this one, this one, this one, and this one, and this one. They are none or nothing. There is no value. Okay. But we still need to have them in order to check what is the last value from the node, from the internal node. So using this binary search tree with the keys, okay, we can use the in order traversal. Do you still remember in order traversal? Okay, we follow the left part. So from here, we go here, and then here, 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 and here. So the in order traversal of a binary search tree visits the key in increasing order. So we will do the traversal from the smallest value 1 and then 2 and then 4 and then 6 and then 8 and then 9. So this is the in order reversal. Oh, okay, let's have a break. Okay, I will continue after the break.